Okay, let's get started. Welcome back to computer graphics, and today we're going to look at the software that you're going to need for OpenGL and the download and what you're going to need to configure your computer with. And I'm going to do it on a Windows machine. And we're going to look at an introduction to OpenGL as a programming interface, an API for computer graphics. So let's see what we've got going on here. In the in the computer graphics class notes, here, if you go into computer graphics here, and by the way, we are starting the class at 5 from now on. So, if you click on software install, you got some handy dandy notes, and the notes are going to walk you through it, but I'm going to show it to you right now. So, out in a Windows prompt, you're going to go to, and I put it in here, so big stuff so you can write it down. Otherwise, it's also in the notes, and you can get it from the course notes that I just showed you a few minutes ago from bhacker.com. We're going to install what's called a Bloodshed Dev C++. If you don't have it already, you can't. You can probably do this with Microsoft Visual Studio.net. You could probably do this with other compilers. However, I recommend using Bloodshed because it's easy. It's very straightforward. It's very easy. And you might want to use this browser. You might want to use this for C++ in general, or C and C++. So if you go to this URL, if you just go and type in from a Google prompt, you type in Bloodshed, it'll take you to this website here, Bloodshed Software. And what we're looking for, this is free. It's free software. You should not have to pay anything for it. I'll make this a little bigger so you can read what's on the screen here. If you go down to the bottom, it says go to download page. That's what I'm clicking on. And if I go to download page, then it says download. I can get it from search source version 5 as an example. If I click on it, it should give me a file download. I actually have it downloaded already, and I have it installed already. But the install is quite simple. I don't want to really go through it again. Actually, you know what? Let me do it. I'll go through it again. It's worth the experience, actually. So let me start the download. Let's see. Hopefully, I have the internet access for it. If I don't have internet access for it, I'll leave it. Supposed to start in 0 seconds, but I don't see it downloading. It says waiting. A little screen should come up. Actually, is what I'm waiting for. The internet access has been kind of buggy, so I'm not quite sure if I'm going to get it. So, if not, I'll have to do it next week. Start in 0 seconds. Problems with link. Please use the direct link. Supposed to. I think my this was the direct link. Let's see if it starts now. Come on, download. Up. No, here we go. Here we go. Okay, so I'm going to download 4992. Actually, that's a more current version, so I'm going to save it. And right now I have it being downloaded. And going down right here. I'm going to remove this actually because I have it on here already. So let's see. It's just a second. Let me just go to Control Panel and remove it. There we go. Oh, I had actually I think I had that version. Oh, it's okay. It's worth having you see it, actually. Okay, do you want to remove the remaining configuration files? Yes. And it's been uninstalled, delete, doesn't contain, okay, that's great. Okay, good. Alright, so we uninstalled it. So now you're going to see it fresh. Alright, so this looks pretty good. So I'm going to click on the downloaded file that I just downloaded. Make this a little bigger so you can see it. That way I can put this out on YouTube and people can download it, install it, and can configure it at home so I can see it work completely. Welcome to Dev C++ install program. Yes, we do want it. You can't install it over a previous version, as that dialog I kind of clicked on it kind of quickly. You have to uninstall it before you reinstall it again, especially if you try to do an upgrade. Not quite sure why. It just doesn't like to be installed on top of itself. So I'm going to select English as the default language. Looks like I've got some other choices, but English looks good to me. So I'm going to say OK. And I'm going to say I agree to the GNU license, and I'm going to download everything and the full components. So just whatever the default says. I'm going to go next. I'm going to put in the dev C++ directory. I'm going to go next. And then I'm going to run through this little install here. It actually runs pretty quickly. It's not too bad, considering this is also in a virtual machine inside of on top of a Mac, so it's running pretty quicker than I expected. Do you want to install the C++ for all users on the computer? Sure, why not? So, and I'm going to set finish, and it's going to bring up dev C++. And I'm going to zoom out a little bit so we can kind of see what this says. This is the beta version. Please report any bugs, yada yada. Okay, I'm too impatient, so I'm going to say okay. Now, the first time configuration, you want to do this because it'll make the program run faster. What this will do is install pre-compiled headers for you. So we can install it. I'm going to use the XP theme, so it changes my Windows motif to a XP looking motif. And I'm going to have English, which is the original configuration. I'm going to say yes. And here's what it says. I want to use this feature. This feature to retrieve the information from header files to find the functions, classes, variables. This will actually speed up the workings of your system. So I'm going to select this option that I want to use this feature. And this feature is basically going to make the headers, going to give me access to precompiled headers, so I won't have to compile them every time I use them. Which is kind of a standard feature you get in Visual Studio. So I'm going to say next. And I'm just going to use the default directory, so I'm just going to go next. And then here we are, we're parsing it. We're going to make the header files available to us. We're copying, you see the .h files are the ones that are being copied to include. Parsing it, essentially. What it's doing is just getting a list of everything there and finding the precompiled code to it so we can link it automatically. So don't worry about it. If you don't understand what it is, just select that option. It'll make your program run faster. And this will take a few minutes before it finishes. And you'll be amazed how fast and easy it is to actually work with OpenGL in this compiler. In fact, the next couple of steps are really easy, actually. But in a few minutes, it will finish. Hello. We are installing the software needed for this course, just in case you're wondering what's going on if you walked in late, which is the dev C++ compiler plus the OpenGL libraries. We're going to configure it. We're going to run Hello World, actually. Actually, we're going to run something better than Hello World. So. And you'll see how easy it actually is. And you want to do this within the next, I don't know, a couple weeks or so, especially if you want to try out a lot of this stuff in the lectures and do the homework assignments for the course. Next week I'll go over the first homework assignment and start showing you examples. But we have to talk about OpenGL before I can start doing that to get it installed. So let's see. Got a couple more minutes here. I'll be patient. Let me zoom out a little bit so I can see what's going on. Eventually, what ends up happening, I'll just leave that alone for a second. We'll get a little. Oh, we got it over here. Okay, already. We'll get a little icon down here for dev C++. You can't see that. It's right here. Actually says dev C++ on it. So it may also put something in the startup menu. Let's see if it did actually. Yep, here it is. Bloodshed dev C++. Actually, I already installed this from the oh, this was here from a previous install, but I'll reinstall it, so you'll see it. So in a few minutes, this is going to finish, and then we can move on to step number 2. This is where I got it. So you can pause the video or write this down or go watch this later. Or get it from the course notes, and you'll be able to find that software that I just installed. And you might want to use dev C++ for other things, you know, like other C++ projects as well. So according to our instructions, we wanted to download and install dev C++, which I just did a few minutes ago. And then we're going to go open up the dev C++ tool and go to Tools and then check for Update Packages. So let's see. I'll go back out here and see what's going on. Oops. Don't need this one. I believe we're still working here in the background. No, it's not hung. It's good. It's still working. A lot of headers, a lot of header files. This is going to be all of our libraries, basic built-in libraries. So I'll be patient. I'll give it a few more minutes. Looks like it's almost done. Here we go. Ah, there we go. Finalizing. Amazing what a little patience can do. There we go. So it says we're done. I'll zoom out so I can actually see the screen. I'm going to say OK. This back is a splash screen for the program. It says it's loading. First time it loads, it actually takes a few more minutes. I'm not going to display these tooltips or these helpful hints. So let me back out a little bit so you can kind of see what you get. When you, and I'll do this one more time so you can see. When you click on this bloodshed icon down here, you're going to get this little splash screen for a few seconds. And then it opens up, and this reminds me of the old days when VisualStudio.net didn't include the .net. It was just Microsoft Visual Studio, and it was a really easy interface. In fact, you can go File, New, you can create a new source code file. Let me just zoom in a little bit so you can see what I'm looking at here. The menu is kind of easy. You can go File, New, Source Code, File, Project. Projects is going to give you, DOS console application, Windows application, DLL. So it's kind of nice. It's a very simplified version of a free compiler, and it comes with a GCC compiler, so you can you don't have to install anything outside of Dev C++. So what we're going to do is go to Tools, and we're going to go check for updates and packages, because right inside of Dev C++, we're going to install the OpenGL. So I'm going to check for tools and packages, and we want to check, this by default is going to be where we got it from actually. The next one down here, the devpacks.org community dev packs is what we really want. So I selected it. It's already there from the drop-down menu. And I'm going to select down here the check for updates. What this is going to do is go out and kind of find out what's new, what I don't have, and status disconnected. Oh, great. Oh, here we go. Oh, good. I was thinking maybe I lost my internet connection for a second. These are all the extra packages that aren't installed by default. So I'm going to sort this in ascending order. So you can see now I have ACE and AGRIF, whatever. And I'm going to basically just go in and select, in fact, if you want to do like movie compressions and stuff like that, use all of the open source libraries for tons of development stuff actually. These are just tons of toolkits and stuff to use. We want two in particular. We want Glut. Here's Glut. I want this one here. And the tools here, let me bring it back out to here. I thought I had it up. The instructions, let me go back to instructions. There's the instructions. From the instructions, I went to inside of Dev C++, if you remember, I went to Tools and I went for Check for Updates and Packages. And then click below the Select Dev Server, which is what that one was by default. And that's where I selected that devpack.org community dev pack. And then I clicked on Check for Updates at the bottom of the page if you don't know, if you didn't catch that. And then once it's done loading, what you did, scroll through the list of the packages until you find the Glut package is what we want. And once you're ready, check the small box to the left of the name, download it, and then your computer will install it automatically. Now you can open up, now you can have OpenGL, comes with Dev C++ and Glut. Try it out, go to File, select New Project, then select Multimedia tab, then select on Glut or OpenGL. So I'm going to actually install OpenGL as well here. So I've got Glut, revisiting the instructions. I'm coming back to the screen where I have the tools. So I'm going to click on the box next to Glut. And I'll explain Glut in a few minutes when the lecture starts. I'm looking for OpenGL is what I'd like. I don't see OpenGL as part of my list. It could just be Glut now, actually. Open layer, no? Python's in there. Oh, Python's in there too. Okay. Well, I'm going to just select the Glut then. And then I'm going to go download selected. They could have combined the packages is what I think probably happened there. And it's going to ask me, this is welcome to the dev package wizard. install Glit, the OpenGL utility toolkit. So it's actually not called OpenGL anymore, it's called Glit. So it's probably a good thing that I went through these instructions so you can actually see what the modern day, because what I had on here was from the last time I taught this class a couple of years ago. So I'm going to say install. Glit has been successfully installed on your computer. Press finish. So press finish. Now I can actually close this window. And then you're probably wondering, well, and actually, you know what? When after I install stuff, I like to close things anyway and open it back up again just to make sure that menus and things get updated. So I'm opening up Dev again, and I'm going to go into the menu and see if I have it. Let's see if I can use it. So if I go File, let me make this bigger so you can see it. File, New, Project. And the instructions alluded to this Multimedia tab. We have an Introduction tab, which is quite interesting. We can run Hello World if we want. And let's say you're brand new to program. Let's just do this for a second. And you say, well, let's run Hello World. And I'm going to call it Hello World. Let's say this says save over here. And I go, oh look, Hello World. Zip out. It's actually kind of easy interface because then you can go like, let's say execute, compile and run, and let's just call it Untitled, just for the sake of calling it something. Little screen comes up, and a little error message. No resources. Oh well, error 1. It's because it doesn't do anything. Program's not compiled. Let's get rid of. Interesting. It comes with it, and it won't compile. Oh, no, it is done. It did compile. All right. Oh, you know what? I was probably running low on resources because I have this in a virtual machine. I don't have very much RAM on here, actually. So and that was unrelated. That was my operating system error. Okay, so now I got Hello World. Press Enter to continue. So I can kind of test the compiler with Hello World if I'm really concerned about it. But what I really want to do is kind of experiment with. So I'm going to close this actually. I'm going to just close all. Let's close it. And I'm going to try and find a new project here. I'm going to call, and I'm going to say, oh, I want to use the multimedia stuff. So I'm going to go File, Project. And now I'm going to click on this tab here that says Multimedia. And now I've got Glut, OpenGL, OpenGlut. This is actually kind of old. This didn't, I downloaded this and installed it separately. But this is what I just installed a few minutes ago. So I'm going to make a basic Glut program. How's that? I'm going to call it My Glut. You'll see what this does actually, and we'll see how powerful this can actually be. This is going to be a C++ project. I'm going to say OK. Close project 1 and start a new project. Yes. I thought I closed that a few minutes ago, but I guess maybe I didn't. And I'm going to call it My Glut. OK. And this is going to be saved in the C directory by default. And these are the other projects. In fact, the projects that you're creating have a .dev extension on them. Not like a Microsoft project where you get the VPROG or something, or PROG. This is DEV for dev. So, and this is going to be a dev project down here. So I'm going to say OK. Now I have a free Glut shapes demo, which brings up, and you can kind of see where, well, what is this Glut library? Well, it's an OpenGL library. So the program is a test harness for the sphere, the cone, and the torus shapes in free Glut, which is what we've installed. And we have a spinning wireframe and some smooth shaded shapes are going to be displayed until the escape key or the Q key is pressed. And the number of geometric stacks and slices can be adjusted using the plus and the minus key. So we've got keyboard input here. We can use the keyboard, and we're going to see, actually let's just see what we're looking at first, and then we'll see how easy it is. So I'm going to compile it, and I'll just call it that's, yeah, just overwrite it, I don't really care. So it should, okay, I don't know what this down here was. Let's just see if it runs. How do you want compiled? Let's see what's going on here. Anchor error. Well, let's see. I'll go to DOS real quick, actually. let's see where I am on here. This is going to be under program files, I think. Actually, let me do this. I believe it created the executable file. I don't know if the problem is going to be with my computer. It may be that I have to reboot after I've installed it in order for the libraries to be in the path, and that will be the next thing I check. But I want to see if we actually have the executable, and if it's so, it's going to be a problem here. No. Oh, no, let's see. Dev C++, here we go. This is where I wanted to go. Project 1, because we should have an executable project out here. Get smaller so I can see it here. Test OpenGL.dev. No, I don't actually see the executable. Oh, no, I don't see the executable file for it. So I'm going to say it probably didn't compile correctly. So I'm going to do another thing here, real quick, just to make sure. I want to try one of the other project types. Well, that one compiled. Okay, so let's see. Let's execute run. Okay, well, here's one of the other projects, and I selected the OpenGL option, which tells me that I'm probably going to need to reboot this in order to get the directories to show up, because it was looking like it couldn't find the library correctly. But this is an example of what the OpenGL is actually doing. This is a spinning triangle or object that's being created. But let me try something else before I totally give up on this. I'm just going to take a few minutes so I can actually reboot this without... You can see how this virtual machine actually runs. This will just take a minute. It's worth seeing it run, though. In fact, this is good troubleshooting because you might end up with the same problem. And then if that's the case, then what I'll have to do is sometime between now and next week figure out, well, what was the problem? Troubleshoot it for you. I believe it's either going to be due to my virtual machine environment, or it's going to be the fact that I didn't reboot the computer. Because I did add some stuff to the environment variables, and in the virtual machine environment, it may not necessarily have worked the most optimally. Let's see. I'm starting Windows again. Believe it or not, this actually runs faster than it does on a computer. See how fast Windows boots. Not too slow. That's because nothing's really loaded. And because it's running in a virtual environment, it doesn't need antivirus software or firewall software or anything, so it's a pretty stripped down version of Windows. But I would like to see the Glut library work. So I'll take a quick peek and see. I might have to change some paths or something. I'll troubleshoot. If it doesn't work, I'll troubleshoot the problem for next week, and we'll just talk about OpenGL. Start the beginning part. Yep, Adobe. Let's not install it. Okay, so I'm going to repeat the steps again. The file, new, project, multimedia, what? Okay, I'm going to call it project 1, just to be on the safe side. You know, overwrite it, yes, overwrite it. And compile. Yeah, just save it. Yeah, overwrite it. And define reference. Let's just take a look, real quick. No. Okay, I believe I'm going to need to troubleshoot this a bit further. It's kind of interesting, the other example actually works. And this says it's actually compiling. Actually, that time it did compile. Let's see if it'll run. No, project is not compiled. I'm getting some linker errors, which means the code's good. It can't find the library to link in the code that it needs. So I'm going to need to troubleshoot that a little bit and find out why that's happening that way. I'm going to try one more thing, though, just because I'm kind of curious at this point. OpenGL. Okay. I'm just saving it all as the same project. Well, that's interesting. The two that I didn't download actually work. So anyway, this is an example of some of the one that I'm trying to run is slightly different. It has some shapes that I can move with the plus and minus key. But this is what we're building in this course. These are, like, as an example, some of the shapes. And you'll see how we can get animation, we can see how we get rotation, and we can actually build some pretty interesting shapes, which is what the OpenGL function calls and the libraries are doing for us. And I'm going to try one more thing, actually, before I give up completely, because I'm stubborn this way. I just want to see if I've... I just want to try to download it one more time, just in case something happened. Oops. Make sure. The Glut should run, though, which is kind of weird that it doesn't. What? Let's see. No. Okay, good. Just want to make sure. Actually, there's probably a bug fix or something online. I'll have to figure out what it is. But, I'm waiting for the OpenGL as well. Yep. All right. Just download it again one more time. Okay, install. Okay. Just try one more time because I'm stubborn. Actually, before I get too stubborn, let me just check something out real quick. I have multiple libraries installed on this computer, and I'm thinking this one is the one I'm going to need to use. Your other one, I should have uninstalled the other libraries. What I should have done, but let me just check out something real quick. Copy. It's just. Yeah, I probably have a conflict with both libraries installed. But let's just take a look here real quick. No, something else. What is this? Interesting. Okay. Just see if I see it real quick. No, it's the precompiled library here. That's the issue. All right, well, I will troubleshoot this for you, and we'll figure out what this problem is. And in the meantime, you might be able to install the Dev C++ compiler, do what I did, install Glit, and we'll see. And then next week, I'll have a fix for you on this, and we'll see this example work. But there's definitely either something that is conflicting, or something that's not set right in my environment, so I'll have to spend some time. I don't want to do it right now. So. So, bad demo. I'll have to do the demo again. So, but any questions upon about what it is you're installing or why you're installing it? Basically, you're installing this dev C++ is a GCC compiler, essentially. You can use other compilers if you want. The only problem is you have to manually install the OpenGL libraries. The reason why I like this one is because of that option in the tools to install it. However, unfortunately, when you try to demo stuff, it doesn't always work. But it's interesting that it's finding and it's just having linker errors, undefined reference. So it definitely is having an issue. I probably have to make a path environment variable change. So I'll fix that. Next week we'll revisit the demo, essentially. But when it's working, it's actually quite nice. And it has to work in a Windows environment. You would have to use different tools on a Mac. And perhaps next week I'll demo the Mac version of it. But Dev C++ is only supported on a Windows machine. So, and because I can't really demo it, I think I'll start in with a different lecture today instead of doing the introduction to OpenGL, because we can't see it work. So I'll shift gears a little bit and I'll go over lecture 2B instead of 2A. So the goal next week is to go over OpenGL. So lecture 2B is on image formation, and lecture 2A is a 3-part lecture that covers everything you ever wanted to know about OpenGL. But we don't have anything to demo with. This is the tutorial on OpenGL, which is about 106 slides. So if you want to preview it, there's a lot of stuff in here we can try out and we can start doing, but I need a compiler running on my system in order to demo it. So I'm going to save that till next week. I'm going to troubleshoot that and get that fixed. In the meantime, if you have the same problem, don't worry about it. I'll have it fixed for you next week. So let's switch gears and talk about image formation today. How's that? Which is an underlying concept that makes sense in terms of what we're trying to accomplish in this course. So the objective here, look at the fundamental image notions, the parts of a world, the parts of the graphics that we're actually programming in OpenGL, some physical basis for the image formation, color, light, perception, these concepts, and then the synthetic camera model, and then some other models to kind of compare that to. So image formation. In computer graphics, we form images, which are generally two-dimensional, using a process analogous to how images are formed in the physical imaging system. As we saw in actually the OpenGL library, those were three-dimensional. Those were 3D graphics. If you noticed, the triangle was actually spinning, if you saw that. It was a wireframe of it, which was just the outer circling, and then it was filled in. It was filled in red in one of the examples. It's just basically two function calls. It's going to be extremely easy for you to actually create something like that with a couple of different function calls. And next week I'll have some examples that are going to run in OpenGL, and I'm going to be able to demo that stuff to you. But what we're looking at is the concept of cameras, microscopes, telescopes, human visual systems that kind of identify objects in space. And a lot of people like to refer to this as a world. So a lot of times we create worlds. Worlds are scenes. Some people call them scenes. I like to actually use the word world. So you can create a world, and a world is a beach. And the beach has sand, and we have water. And it's really just painting a scene, creating objects and putting all the objects in the same world, and then applying light to the objects, and then orientation on the objects. So the objects are facing a certain direction. The objects are sometimes on top of one another, or they overlap, and they create some interesting illusions. So elements of the image formation, we have the objects, and those are everything that appears in the scene. We have the viewer. How are we going to view it? It's orientation. In terms of, are we looking at it face on, are we looking at it from above downward, or from downward to upward? And then we have the light sources. The light source doesn't have to be at the same spot as the view, which is kind of interesting. We can look in on a scene, let's say for example going back to that beach, and the light could be in the upper left-hand corner like the sun, and the sun can actually be shining in our viewpoint, in our eyes, or it can be shining on objects. And we create the illusion of the sun and the lighting through the use of shading and viewpoints. So from this particular view, if you were looking at an object that was in direct sunlight would have a shadow casted behind it. And so from our viewpoint, depending upon where we're standing, the shadow is going to be at a different location. And the shadow is going to look different. So we apply an algorithm to it to determine where the shadow is supposed to be, given a certain viewpoint and a light source. And then we have different kinds of light sources, which is kind of interesting. We have light in this example of this particular room. We have illumination, where you can actually kind of see it. And these are kind of the little details that you fill in when you're creating realism. As an example, if we were just to light up this room, we wouldn't see any of the shadowing, and we wouldn't see any of the effects. As an example, as I'm standing right here and I'm looking back there, those walls are darker than these walls over here, which we don't really think about in our normal day-to-day life. You know, it's like when we look around, you know. But we have actually over here we have some shadows being casted, and it's because of the directional light source and the type of lighting that's in this room. So what we try to do in computer graphics is put all these concepts together and create a world or a scene that represents reality. And this is where you get some that looks real and some that doesn't look real. And so in order to understand how you're going to make it look real, you have to understand the underlying principles. So here's an example. We've got the viewer that's coming out in this particular depth, and we're looking at that particular way that the view is being casted from our orientation of left to right, and the top down. And then we have a light source up here that's going to illuminate objects, and you can kind of see where this is dark and we see a shadow here because the light's over here. This we actually have to apply a light source to an object, and then we apply it to other objects. Where most people go wrong is they don't apply it to all objects. So one object has a shadow and then there's something next to it that doesn't have a shadow. And that's when we can look at that and go, something's wrong. Something doesn't look right. And then we can figure it out. So attributes that govern how light interact with the materials in the scene are important. And then note the independence of the objects, the viewer and the light source. All of them are independent. All of the objects that we put in the scene are independent objects we create. In fact, this particular object can be 1, 2, 3, 4, 5. It can be like a dozen or so different objects that are all oriented, so we can have layering on a flooring, a wall, a ceiling. There can be all different objects, pieces of objects that come together to form an object. So let me take a few notes here on the light. Light's the part of the electromagnetic spectrum that causes a reaction in our visual systems, causes interesting effects. Generally, there's wavelengths in the ranges, and long wavelengths appear as reds, short wavelengths as blue. So the shadowing, color, the way that the light dissipates from distance, through distance, is kind of interesting to apply. We have the concept of ray tracing and geometric optics. Okay, so OpenGL does not perform ray tracing. Ray tracing is sort of an advanced concept for which there's a lot of research out there for people who are looking at ways of performing ray tracing in an effective manner. So one way to form an image is to follow the rays of light from a point source, finding the rays that enter the lens of the camera. So as the word actually kind of describes the problem with ray tracing is if you're going to follow the light source and actually predict through an algorithm technique the shadowing and how the light affects every single object, that's a lot of processing. So instead we do manual techniques of kind of, appearing. As an example, if the light's up here, we see that there's no shadow over here, but we have a shadow here and a shadow here and a shadow here, and the shadow actually gets rotated a little bit depending upon the angle. So each ray of light may have multiple interactions with different objects, and objects might actually have another interaction with another object before absorbing or going to infinity. And that's the interesting thing, is we have objects that absorb light and that become illuminated themselves. And then we have objects that don't absorb light. And the interesting thing is, you said, you can say, well, how do we make something look metal? We cast a light source on a metal object, it illuminates, it absorbs it. So we want to make it look like metal. we apply some illumination, which is coloring, if you think about it. So the coloring, the shadowing, the light, how the light dissipates and how the light gets followed from object to object, makes realism in the scene. So these guys who get paid multi-million dollars to put together these animated scenes that look real, yeah, probably you're starting to imagine, hopefully, there's a lot of work that goes into that. There's a reason why they get paid millions. Pixar is the reason why these guys get paid a lot of money. And there's a reason why the scene actually looks quite real. They're really taking this to an extreme. Luminance of images, monochromatic values are gray levels in terms of grayscales, analogous with working with black and white film of television. And then we also have the color image concept. These are just some vocabulary and some words for you. Has perceptual attributes of hue, saturation, and lightness. So we can apply saturation, hue, we can apply these things, and we can run functions that create the effect that we're looking for with OpenGL rather than having to do it manually. Which is the beauty of OpenGL, is it actually does a lot of this stuff for us. You have to match every frequency in the visual spectrum. No, you approximate. And you have algorithms that run that do some approximate matching for you. So we have a three-color theory that we're working with. So human visual systems have two types of sensors. We have rods and cones. So the rods are monochromatic, night vision. And then the cones are the color sensitive. Three types of cones, only three values that are sent to the brain. So in working with the concept of how we actually see color, we translate the color options and the settings with the OpenGL library into things that we're going to be able to pick up by the human eye. Because why should we go further if you can't see it? So we're only going to make what we can see, essentially, theory, which is kind of the concept of computer graphics in general. If the monitor essentially isn't going to support the resolution for the level of detail, then you approximate and you make it so it looks good, in terms of what it is you're looking at. You only match these three values. You need only three primary colors. So you get the Rgb, the red, blue, green scale, which is where that comes out of, actually, the three color match scale. I mean, just like you've seen computer graphics with, if you've done any web development, worked with Rgb Colors, then you've seen this is pretty much the same concept. And here's our RGB, our red, blue, and our green, in terms of our triad of colors that we're working with. And here's a shadow mask of a CRT where we've got a blue gun, or green gun, and a red gun going through a mask that projects color combinations. So just the same way, if you remember, if you've done any painting in your life, like painting with colors, you can take the primary colors and you can mix them. You can come out with purple, you can come out with pink, and all sorts of different color combinations that you can paint with. In fact, all colors come from those three combinations, and that's what we're using in terms of the low-level abstraction. So additives and subtractive colors. And so actually this is pretty much how the CRT masks work, actually. You project combinations of the red RGBs through pinholes, and you reflect it on a surface, essentially, and the surface is viewed backwards by the user. So it's kind of interesting how that works. Additive colors. So form a color by adding amounts of three different primaries, and this is what I meant by the old painting days. You took some paint, you mixed it together, and you came up with these colors. So CRTs, projector systems, positive film, primary colors are red, blue, and green. This is red, red, green, blue. I like to say red, blue, green for some reason. RGB. Well, so I have it backwards. I always say RBG. It's RGB. Sounds the same if I say it 5 times. Subtractive colors, they form a color by filtering the white light with cyan. So we have C, magenta, M for magenta, C for cyan, Y for yellow filters. So we can apply filters to it. We can actually get different combinations. So we have light material interactions, printing, negative film. All uses those color bases. So here's our pinhole camera. Uses trigonometry to find projections of points from the XYZ plane. And this is an interesting thing, and this is where geometry comes into play. We really are working on an XYZ for two-dimensional, well, for 2 and 3-dimensional for some purposes. Otherwise, you know, we have to have that Z-plane in order to get past the flatness of the image. And we can rotate objects on that plane, and we apply pinhole lighting as a concept in terms of a pinhole camera. We apply to it to see if I were to flash lights, illuminate light, like if I had a flashlight and I were to walk in with a flashlight and I were to hold at a particular angle from realism, where would the light go to? What would it illuminate? And so that's where we can get our illumination. So there are equations of simple perspectives to be used. And lucky for you, you don't have to do this manually. The OpenGL library does it for you. So that's why I can't wait to show you the OpenGL library. So, synthetic camera models, we have a projector. So we have an image plane where we have a projector of P in the center of the projector. So this is kind of like how projection systems actually kind of work, where we have a model, an image, and it's illuminated and increased in size as it gets further away from the source. So it gets projected essentially through a plane, and so we can adjust the XYZ plane, and we can warp this. We can put it on its side, we can move it around all over the place by adjusting it on the plane. Advantages. The separation of the objects from the viewer from the light source gives us flexibility. We can add objects to the scene, we can take objects, or we can animate objects in the scene, and we can apply the light source to it, and then also the viewer perspective. Two-dimensional graphics is a special case of three-dimensional graphics, and what we're talking about is actually the two-dimensional graphic plane. We're going to hit three-dimension after we talk about basic concepts. Leads to simple software APIs, aka OpenGL. So you can specify objects like camera attributes, let the implementation determine the image, leads to fast hardware implementation, utilizes a better optimization of the algorithms and the techniques that work directly with the hardware. Global versus local lighting. This is interesting. You can have multiple light sources. You can have, as an example, in this room actually I can turn on a cell phone and have a light coming from the screen. It's going to be a different light source than the light that's coming from the ceiling. It's a different light source from somebody else's phone that they might turn on. You cannot compute color or shade of each object independently. It's a little time consuming. Some objects are blocked from light. Light can reflect from object to object. Some objects might be translucent, might be see-through objects, which is interesting because what you can do in terms of, we talk about optimizing the processing and making the scene paint faster. Well, you only paint what's visible. So if you have a 3D object, you can't see the backside, you don't paint the backside. It never gets calculated. Or if you have a light source that's blocking out certain objects, you don't paint those either. What I mean by paint means you have to process, run it through the graphic pipeline to actually make it visible for the user. But if it's not visible, why do it? So older systems didn't take that into consideration and would paint everything and then just block out what you couldn't see. A little time consuming if you think of the concept. So why draw a huge picture of something and then take black paint and wipe it all out because it's in the dark? You know, it's just kind of a waste of processing, a waste of time painting. So why not ray tracing? Ray tracing seems more physically based, so why don't we use it to design a graphic system? Possible. It's actually simple for quick objects such as polygons, quadratics, simple point sources. In principle, you can produce global lighting effects such as shadows and multiple reflections, but ray tracing is slow, not well suited for interactive applications. As I mentioned before, ray tracing is time consuming for the computation, and you would sit there playing a video game and it would move in slow-mo. using the current ray tracing algorithms that are out there, which is one of the current areas of research that's still going on. And you'll find OpenGL implemented ray tracing utilities, libraries, that kind of work right at this point. They're sort of semi-functional, but they're not really put into production yet because, again, it's a lot of calculation. If you're going to, I mean, it gives you more accuracy, gives you better resolution, fixes the problem of independent objects, it treats the entire scene as a whole. Only problem is your game isn't going to run right. Your video game, you're going to use OpenGL. In fact, I'll comment on OpenGL. It's used for a lot of video gaming. It's used for a lot of game applications, computer animation, and in terms of animation, you're going to make it non-functional if it is too slow. Oops. So I got some time left, so I'm going to run through just the first part of a couple slides of OpenGL to kind of start this lecture, and then I'll troubleshoot, and I'll show you the source code examples next time. We've got about a half hour left. Tutorial on OpenGL. Alright, so this is what we're going to cover next. I'm going to finish this next time. It's 106 slides, we're not finishing it today. The development of the language and the API, the architecture, the concept of the state machine functions, types, formats, and a simple program. So the objective here. So what is OpenGL? Low-level graphics rendering and image library. Only includes operations which can be accelerated, which means it doesn't include some basic stuff that hasn't been experimented. In fact, OpenGL essentially is very experimental at this point as well. A layer of abstraction between the graphics, the hardware, and the application program. The API produces high-quality color images and 3D objects. And actually, as we've seen from a couple of little examples from the Hello World graphic projects that I opened up a few minutes ago, they're pretty sophisticated for a graphics library. So a procedural rather than a descriptive graphic language, an operating system and hardware platform independent. So it actually works on the Mac OS X. Different library. Works on Windows, works on Linux, works on X Windows, works on all sorts of different platforms. And the APIs can be installed for every one of those different platforms. Maybe I'll get it working on the Mac. How many people actually work on the Mac? You guys work on Mac? Windows? Windows? Windows or Mac? Linux. Oh, you know, Linux and Windows, it's going to be the same library. Actually, you can install, I believe you can put Bloodshed on Linux as well. Do you have a Mac? What kind of Linux do you run? Ubuntu? Oh, you're hardcore. Okay. Alright, so nobody here is on a Mac system, so I don't know. If I find it, if I want to put it together, I'll put a little tutorial together on that. But I'm not going to waste too much time on it then if nobody's using it. So, OpenGL features, let's talk about the features. Texture mapping. Well, that's kind of an interesting concept. We can take an image, let's say one of these desks here. You know how we have laminate, because I know that's laminate, that's glued on top of particle board wood or whatever, holding the surface up. It's kind of like texture mapping if you think about it. You take a picture of wood and you glue it. Well, okay, you project it, you fill the image onto a surface. And the surface is the shape of the object. So you can take and create a laminate flooring by taking a picture of laminate wood, applying it to the surface, which is kind of interesting because then you can take pictures of people, faces of people, apply it to 3D objects of faces, and you can create a pretty human-looking humanoid, which I actually have one example I'm going to show you of a humanoid. One of the assignments actually is going to have you create a humanoid. But we'll play around with texture mapping a little bit. Z buffering, double buffering, that's going to a lecture in itself on buffering and that concept. Lighting effects, and the buffering is actually going to give us our animation. It's going to give us our speed in painting. If we can buffer stuff, which means we bring it up, get it ready, then we display it. So we can build an image before we actually project it, before we actually put it out in the world. Lighting effects, I just talked about that. Smooth shading, texturing. Material properties, making something flat, making something shiny. If you think about that concept, we have this in everyday life. We have surfaces that are shiny, metals that are flat or brushed look. We can create that in computer graphics. Alpha blending, transformation metrics. Transformation metrics will be an entire lecture in itself, actually. And that's basically how you take an object and you transform it in the XYZ plane to essentially turn it on its side, turn it upside down, do all sorts of different things to it in terms of the view perspective. Texture matching. Let's talk about that for a second. The ability to apply an image to graphic surfaces. So we use it to rapidly generate realistic images without having to specify an excessive amount of detail. So create a wood floor by painting the floor's rectangular surface with a wood grain texture. We actually take pictures of wood, and we we apply it to the frame. So Z buffering, and I'm going to just basically go through these definitions. The ability to calculate the distance from the viewer's location, how far away is it. It's interesting if you've ever noticed how perception takes things that are farther away and makes them smaller than things that are closer up. We have perception or perspective to actually consider. Most people don't realize this until they take a photography course and they start looking at down a hallway. You get about 20 feet away from you and the objects appear kind of small back there, which is essentially what we're doing with Z buffering. We're making it in perspective from the distance of the viewer location. Make it easier for the program to automatically remove surfaces. So that's what I was saying before. Parts of surfaces that are hidden from view, why paint them? Why bring them up if you don't have to do it? So it makes it load faster. At the start, you enable a Z buffer, and here we go, GL enable, which is a function call, and we're going to use this variable as the Z buffer. For each drawing, we're going to clear the Z buffer, we're going to clear it, reset it, GL clear, background color, the depth, the bits. So double buffering is another concept, supports smooth animation using two buffers instead of one, double buffering. So draw into the back buffer while displaying the front buffer, and then swapping the buffers when you're ready to display it. So that's what I said, basically bringing it up, loading it, getting it ready, and then when the animation occurs, it's there. So the double buffer allows you to store more than you currently need, so you can jump ahead faster in terms of the image rotation, in terms of the animation. Enable double buffering, you would use an aux-int display mode, and you would essentially turn it on. Your drawing is done in a hidden buffer. After drawing, you swap the buffers. And this can be done for you automatically, actually. And actually, the interesting thing is people who don't like OpenGL, who want to work from it from a higher perspective, you can get Vrml, which is virtual reality. It's a web plugin. You can get a Vrml browser. Virtual reality manipulation language plugin for your web browser that works on top of OpenGL that creates really cool worlds and shapes that's even higher up, that automatically does everything for you. You don't have as much control over the concepts. You don't really learn very much about the underlying computer graphic concepts, but you can create some pretty good stuff. Also, the Android development kit, the Android SDK, works on OpenGL, but it works at a little higher level as well as higher level abstractions. The lighting effects, the ability to calculate the effects of the lightness of the surface color when different lighting models are applied, one or more different lights. 3 steps. You enable the lighting, you specify the lights, you specify the materials. For advanced users, you can have local and infinite viewpoints, 2-sided lighting. You can see it from multiple perspectives as the viewpoint changes. The lighting changes with it. Smooth shading gives you the ability to calculate the shading effects occur when the light hits a surface at an angle and results in subtle color differences across the surface, which is kind of interesting. So take light and shine it on a surface and you can kind of see the coloring change. So that's smooth shading. Effect is important for making a model look real or realistic. And then looking at the concepts of the material properties, that vocabulary, and what I'm trying to do is give you an overview of these concepts before we start implementing or looking at them. Ability to specify the material properties of the surface, dullness, shininess, what you're basically doing is applying a property to it to make it flat, to make it shiny. It's kind of like when you go into the paint store. You guys have ever bought paint before, and you can get shimmery, they have, now as I brought the example up, my mind goes blank. I don't remember paint. You can get shiny surface paint. You can get flat surface paint, so it looks like flat, or you can get like light, not quite very shiny, but slightly shiny, where you put the paint on and it kind of gives you a different texture, different surface. Alpha blending, the ability to specify an alpha or opacity value for additional to the regular RGB values. Transformation matrix. That's the concept of the ability to change the location, the size, and the perspective of an object in a 3D coordinate plane. So you take an object, you write it on an XYZ plane, give it a location, and then you rotate it. And what you're doing is really referred to as transformation metrics. You have a matrix 1, and then you translate it to matrix 2, to matrix 3, matrix 4. And that basically gives you the coordinate plane for the rotation, or for the movement. Because you can have something move across the plane, and actually calculate ahead of time the location that should go to get a smooth movement out of it, or smooth rotation. So how OpenGL works. Same way the GDI, graphic device interface, works. Whenever the program makes an OpenGL call, the OpenGL 32 or GLU 32 DLLs are loaded, if they're loaded correctly, if they're installed correctly, and we're going to see it working next week. Limitations on the OpenGL, Microsoft generic implementation of OpenGL. No direct support for printing OpenGL graphics to a monochrome printer, obviously, or color printer with less than 4-bit planes of color. Yeah, it's hard to print out your OpenGL images. It doesn't print out correctly because we have different view qualities that don't translate correct. Hardware palettes for various different windows are not supported, so some of the different coloring systems may also vary. And some of the OpenGL features are not implemented in terms of, this is the generic Microsoft implementation. When you go out, if you go out and do it, you're going to get Microsoft OpenGL, you'll get this OpenGL, open source, that OpenGL library, and it's a zoo, which is why I like the dev C++. It's easier. It's the open source, real OpenGL base when it works. So it'll work next week. So some of the features are not supported in some of the other ones, including stereoscoped images. This is, if you kind of think about the concept of OpenGL, it's kind of like your different versions of C++. We got GCC, G++, C++, C, Turbo C, Microsoft C. For every one of the C versions, we got an OpenGL version that's kind of similar in terms of concept. Early history of the APIs. IFIPS 1973 formed 2 committees that came up with a standard graphic API. We had the graphic kernel system, GKS, still actually around, 2D, but contained a good workstation model. We had the core, both 2D and 3D, GKS adapted as ISO and later ANSI standards in the 1980s. GKS not easily extendable to 3D graphics, just 2D, so far beyond hardware development. So, very behind. So we had the programmer's hierarchical graphic interface still around, and X still around, arose from the CAD community. Database models retain graphic structures. X Windows system, the DEC MIT efforts, is also around. Client-server architectures with graphics. PEX combined the two, not easy to use. All of the defects of each one of them were included in it, actually. We had SGI and GL. Now we're getting closer to modern day. Silicon graphics revolutionized. So silicon graphics machines, high processors, graphic processors that worked with graphic manipulation. Implemented pipelines in the hardware in 1982. Not too long ago, I guess. Well, 82, I guess, for you guys. It's probably when you were born. I don't know. To use the system, application programmers used a library called GL. So with GL, it was relatively simple to program 3-dimensional interactive applications. Then we had OpenGL. where we're at now. The success of GL led to OpenGL 1992, platform independent API. Easy to use, close enough to the hardware to get excellent performance. Focus on rendering, and I'll talk about rendering in the graphic pipeline in a lecture to come. Omitted the windowing and input to avoid Windows system dependencies. So we don't actually, that's why we use the libraries with C++ to create windows that are, for the platform that we're creating for. So we can use Coca for whatever the API for the windowing system is on the Mac, and we can use MFC window toolkit for the Windows systems, and we have that little separation. So OpenGL, the evolution of it, controlled by the Architectural Review Board. Members include SGI, Microsoft, NVIDIA, HP, 3D Labs, IBM. Everybody's kind of involved. Relatively stable. Evolutionary effects, new hardware capabilities, 3D texture mapping, texture objects for text programs, allows the platform-specific features through extensions. Tons of extensions. In fact, if you hadn't noticed, I had like 3 different OpenGL versions in that dev C++ that I was running. Outside of Glit, we'll get to that in a few minutes. I think Glit's right there. Let's see. So we're getting this to explain what it is you're actually installing. So OpenGL is the core library. The OpenGL 32 on Windows, GL on Linux and Unix systems. In fact, maybe I should see if the Glut actually included GL. May have been that the libraries, I probably didn't install something. OpenGL utility, the glue, provides functionality for the core that avoids having to rewrite the code. Links with windowing systems, X Windows, Macintosh, Glut. Okay, so the Glut library is supposed to give you the OpenGL utility. Provides functionality common to all Windows systems, so it's not platform specific. You open a window, initialize the OpenGL state, get input from the mouse to the keyboard, supports menus, supports event-driven behavior, which is why we're going to use it. The code is portable, but lacks the functionality of a good toolkit for specific platforms, because it's kind of platform independent. Doesn't have slide bars. Not officially part of OpenGL, but it's supposed to be supporting it. It's supposed to be supporting it itself. So what we're going to do, I'm going to stop actually because this is a good stopping point. What we're going to do next time, TA, remind me. Hello, wake up. I'm going to start on slide 24 next time, if you can remind me. Okay, good. And next time I'm going to have an open. I'm going to have a working system for you. I'm going to troubleshoot that problem so we can have something, so I can run examples for you and show you stuff. And it's actually probably a good experience because I know 1 or 2 people in the class are going to run into the same problem. So I might just have to uninstall everything and reinstall stuff all over again. So, and if the Glut doesn't work, which I'm sure I can get it to work, I'll find a backup source for you. Okay, that's enough for today. All right. See you next week, unless you have questions. Nope. And then next week I'll also go over the first assignment as well, because we need something to work with before we can actually start discussing concepts. Okay, see you next time.